Hello and welcome to this new video. So this is the second appendix to chapter 1, Appendix B. I have something to say about the Bolzano-Weierstrass theorem. Okay, so we ended chapter 1 actually with the two corollaries. One of them was called the Bolzano-Weierstrass theorem. Okay, actually both corollaries have the same name. So I will call the first one version 1 and the second corollary version 2. Okay, so version 1 of Bolzano-Weierstrass. Weierstrass was a German mathematician, so it's pronounced Weierstrass, actually, if you want the right pronunciation. Bolzano, I don't know, maybe he was something from Italian, or so maybe it's Bolzano, I don't know. So the first version of this theorem states that every infinite and bounded subset of R has a limit point. Version 2 states that every bounded sequence of R has a conversion subsequence. Okay, so you may ask why both versions have the same name. Why both theorems have the same name? Actually, because they are equivalent. So, and I'm going to prove this in this video. So I'm going to prove how to. So I'm going to deduce version 1 from version 2 and version 2 from version 1. Okay, so they are equivalent actually. So if you prove one of them, the other will be proved. Okay, so let us start with the easiest part. Version 2 implies version 1. Okay, so we have to prove what? That every infinite and bounded subset of R has a limit point with the assumption of the second version. So let A be a bounded infinite subset of R. Okay, now A may be countable or uncountable, you don't know, but at any rate, it contains a countable infinite subset. And by definition, an infinite countable subset can be put in a sequence, and we can remove the redundancy or the repetitions and assume that all the xk in this, so we can assume that all the elements are distinct. Okay, so there's no repetition. Okay, so now we have a sequence actually. So I listed the countable subset of A as a sequence. Okay, so we have now a sequence xn of A. Since A is bounded, xn is bounded, right? Because bounded means that one is bounded from above and below, or if you like, A is contained in some interval CD. So xn will be between C and D. Now, so we are now in the assumption of version 2. So we have a bounded sequence of real numbers. Version 2 tells me that xn has a conversion subsequence that I call x and k, and let x be the limit. So x and k converges to x. I will prove that actually this x is a limit point of A, of the set A, and we are done. Okay, how do I do that? I go back to the definition. So I have to prove that every neighborhood of x meets A at infinitely many points. We know this characterization of limit points actually. So consider a neighborhood U of x. Since x and k converges to x, then starting from a certain rank, k0, all the elements of this subsequence will be in U. So what does this mean? So in particular, x and k0 is in U, and of course it's in A, so it's in the intersection. The next one, x and k0 plus 1, is also in U and in A, and etc. and so on and so on. So U intersected with A contains this infinite set. How do I know that it's infinite? Because there's no repetition in this sequence. All the elements are distinct. Okay, so this now is an infinite subset contained in the intersection. So the intersection is infinite. And this means that since U was arbitrary, this means that X is a limit point of A. Okay. The converse is a little bit more difficult. So let us prove this implication. Version 1 implies version 2. So I have to prove that every bounded subsequence of R has a conversion subsequence, knowing that every infinite subset of R bounded has a limit point. Okay. So let Xn be a bounded sequence of R. And consider the range of the sequence. Okay, here we have to be precise because we distinguish between two things. The sequence itself that we denote between parentheses, which is a list, or if you like, it's a sequence from the integers to R. So we distinguish between the element xn, which is the real number, and the sequence xn, which is a function, if you like, of the integers. The range of the sequence is the set of values taken by the sequence. Okay, now this set, although it's written in this way, but there's no guarantee that xn has no repetition. So actually, this set could be finite. So we have to distinguish between two cases: the case where A is finite and the case where A is infinite. An example of a case where A is finite, just the sequence -1 to the n. Okay, so it just takes two values, -1 and 1. So A is just -1 and 1, which is a finite set. Okay. Now the finite case is easy actually. So if A is finite, first case, so we can list the elements. So suppose that A contains m elements. So we can write capital A is small a1, a2, etc. up to an. Okay. We can assume them distinct, but it's not a big deal. Okay. So the sequence takes, so by definition, it means what? It means that for every n, xn is one of these numbers. Okay, so that there exists, for every n, there exists k such that xn equal ak for some k. And this shows actually that we can write n, or n star actually, because we start from 1, but we could start from 0, it's not a big deal. But since we started with 1, so it's n star. N star is a finite union of these sets of subsets of integers. So if I call this set the set of n such that xn equal k, if I call it capital AK, so I can write n star as a union of capital AK. How do I prove this? Double inclusion. Of course, AK is a subset of n star, so each capital AK is a subset of n star. So the union, okay, so one inclusion is trivial. The second, so the reverse inclusion, take an integer n, small n here. Since xn takes one of these values, so there exists k such that xn is in ak. So xn, small xn, is in capital AK. Okay, so any element here is in some of these sets, so it's in the union, so double inclusion. Okay, so I partitioned my n star into a finite union. Now, since n star is infinite, one or more actually, at least one of the AKs is infinite. Why? Because if all AK were finite, then I have a finite union of finite sets, and this would be finite. But n star is infinite. So one of these, I will call it capital AI. One of these, at least, AI is infinite, right? So what does this mean? It means that I can, so capital AI is a subset of the integers. So I can list the elements in an increasing order, right? Because we know that every subset of the integers, of the positive integers, actually has this smallest element. So n1 is the smallest element. Then take n2 to be the smallest element of AI without n1. So there is a first element, a second element, a third element. So I can arrange or list my subset capital AI into an increasing sequence of integers. Okay. And therefore what? Therefore, by definition, since, okay, therefore I claim that for every k, x and k is equal to AI, right? Because okay, why? So let k be an n star, and k is an AI. What does it mean that nk is an AI? It means that x and k is equal to AI by definition of the set AI, capital AI. So by definition, x and k is equal to ai for every k in n star. So therefore, what do I have? Therefore, I have a constant subsequence, right? In particular, it's conversion to ai, right? So it's a very particular kind of conversions, actually. So the subsequence is actually constant. Of course, we didn't use the assumption because the set is finite, so the assumption doesn't apply. Okay. Now, the more interesting case is where capital A is infinite. Okay. So if A is infinite, A is what, once again? A is the range of xn. So if xn is bounded, then capital A is bounded, right? Because A is, so if xn is, for example, is between C and D, then A is included in the interval CD, right? So A is bound. So now I have what? Now I have an infinite and bounded subset of the real numbers. And so the assumption I am in the assumption of version 1. So version 1 tells me that capital A has a limit point x, right? And now I will prove that there exists a subsequence of xn converging to x. Okay. So how do I do that? Step by step, by induction. Okay. Step 1. Consider the neighborhood of x minus 1, x plus 1, right? This is a neighborhood of x. Since x is a limit point of A, then this neighborhood meets A. Actually, it's infinite, so the intersection is infinite. Right? In particular, it's not empty. So there is an element in the intersection. This element is necessarily of the form x something, xn1, I call it. Why? Because an element in A is necessary, so it's the range of the sequence. So it's equal to some x something. I call xn1, right? So this is easy. So xn1 is in the intersection. Okay. So it means that in particular xn1 is between x minus 1 and x plus 1. Right? Second step, consider a smaller neighborhood, x minus 1/2, x plus 1/2. Okay, since small x is a limit point of A, then once again, call it u. The intersection of u and A is infinite. So this means that I can find elements with arbitrary large indices. Okay, so I can choose an element xn2. Of course, the element in the intersection is in A, so it's necessary of the form x something. But I can choose the index as large as I wish because the intersection is infinite, right? So in particular, I choose the index larger than the previous index that I found in step 1. Okay, if you find this difficult, you can prove it. You can prove this result by contradiction. So suppose that this suppose that there is no n. Suppose that for every n, there's no n in the intersection such that n is bigger or equal than n1. So this means what? This means that if xn is in the intersection, then n is less or equal than n1, right? And from this, it would follow that the intersection is finite, actually. Okay, because the intersection would be contained in the interval 1, etc., up to n1. Okay. Now I repeat this procedure. As step 3, I take x minus 1/3, x plus 1/3. So at the k step, since the intersection of x minus 1 over k, x plus 1 over k with A is infinite, we can choose an element in the intersection with arbitrary large index. In particular, I take an index bigger than the index of the previous step. Okay, so and so on. If I go to infinity, then I would have a subsequence x and k, okay, such that x and k is in the interval x minus 1 over k, x plus 1 over k. So it means what? It means that x and k minus x in absolute value is less than 1 over k. And so as k tends to infinity, x and k minus x tends to 0. So x and k converges to x. Okay, so that's it. This concludes the proof of the equivalence between the two versions of Bolzano-Weierstrass, and this is why they have the same name, actually. Okay, so thank you for your attention. In the next video, I'm going to talk about approximation of some irrational numbers by rational numbers, okay, in a more concrete way. So, and this would end chapter 1, actually. Okay, thank you for your attention.